Welcome to the stream, everybody. I do have some really fun things I've been working on. So you'll notice I got a little bit of a different microphone stand today, and I got something I want to try. And I'm still kind of playing with this idea, but it is using a top down with a whiteboard. And I've kind of done a little bit with this in the past, but I haven't done it in a live setting for sure. And I've been working on how to kind of optimize this. But what I like about this is it opens an opportunity where if I have some parts on a shelf here next to me and we want to do some discussions around that, I can grab my multimeter. We can discuss. Okay, well, hey, we're gonna do. You're asking questions about EXV testing, troubleshooting, something like that. Well, I've actually just happened to got one right here. Why don't we pull it out? Okay, measure this. This is what I would expect to see. Da 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 da. Right? Kind of the high level thought process of what could be done. At a minimum, we do have just the whiteboard itself, where I can doodle draw. Y'all can see my terrible spelling, and I can better illustrate what we're discussing. That's the kind of the idea and the thought process behind it. So, yeah. Fun added feature, call it that, I guess. I don't know. Just something I'm playing with and experimenting. Either way, how you doing? Hopefully you're having a good day. It is Memorial Day, so happy Memorial Day, everybody. You do your own thing. Days off they don't really mean what they used to, So we're here because, well, we do this every Monday, and I figured today, depending on what your Memorial Day looks like, maybe you'd like to come hang out for a little bit and we can talk chillers for a little while. I am down. We have three questions that were in the portal over on chilleracademy.com. So I do prioritize those. If you're not already set up over there, that is the chiller questions answered series. There is a free portal that you can sign up to. Questions posted in there along with pictures. You can post pictures in there. I do prioritize those for the streams, and then we will start there and work our way down the list. So anyway, really excited for today. Hope you're having a great day. I see everybody in the chat. How you doing, Frylock and Froggy? If you didn't just see it, we got a whiteboard today. So if things look slightly different in terms of camera and whatnot, that's because I did some rearranging to fit in the new angles. Now, let's roll into the first question. Okay. Let's go over the female unloader solenoid valve for the Trane CHH, so Trane screw compressor. See attached picture, which we'll get to that in a moment. In what circumstances is the valve in the open position de-energized, right? I understand it's bypassing the discharge gas to suction. Is this valve working similar to how hot gas bypass works? Also, is the compressor in the picture in the unloaded or loaded position? So that's going to be this one here. Okay, so by the way, this picture is in the RTAA just IOM manual. If you ever want to pull this up, read about this compressor deeper and get into it a little bit further, that's where I would suggest you can go in, and it actually does a pretty good job explaining a lot of this and breaking it down. But the female unloader specifically is down here, and it is different from the male load and unload solenoids and valves. Okay, so these up here are what are controlling the slide valve, and that was the second part of the question. We'll get to that. But the first part is primarily focused on the female unloader. So the female unloader is controlling this internal check assembly to the compressor. That is my understanding of what this is doing internally, where these are rediverting, say, oil to push the slide back and forth. The female unloader is actually triggering a type of gate, the way I understand it, internally. And yes, it does function just like a hot gas bypass. It's just internal to the compressor. All of this is inside of there. It is not external. And yes, when the solenoid is de-energized, then this will bypass. And what that means is that it will allow this little gate in here to open, and the discharge gas will flow back into the suction. The whole purpose of this is to unload the compressor. So in terms of when does this engage? Well, this will engage during the startup cycle. So when we go to turn the compressor on, and I think it also it disengages at the shutdown spot as well. So at bare minimum, when it goes to turn on, the first couple of minutes, that solenoid will be de-energized, allowing bypass. Then, after it gets past the startup phase, it will move into a normal, or we want the compressor to begin to load. Then we will energize the solenoid for the female unloader, and when that gets energized, it does block off the bypass internally on the compressor. And at that point, the compressor is able to load and unload normally via the slide valve. Now, the slide valve in this picture is being represented in a loaded state. And if we come over here and look, slide valves will move towards the discharge side. And when a slide valve is operating, it is opening up the suction side of the slide, or of the screw bolts. And that is because we want to reduce how much compression and flow is moving through these bolts. So to do that, we're going to reduce how much suction surface area there is, but we want to maintain our discharge surface area. So in any diagram or depiction of these, you're going to see, now this isn't that compressor. This is a handbell, so in case that's throwing you off, this is not the same Trane compressor, but the same theory applies. This slide is going to move towards the discharge side of the screw bolts in that process. So looking at this picture, this slide is in a fully loaded position, where the little ghosting here would show a fully unloaded position. So if you ever open one of these up, these are really easy compressors to service in the field, and servicing this slide is something we would do. If the slide puck is all the way out to the outer surface, close to the discharge, that is a unloaded slide. And if it's further back into it, which is a lot of times what will happen, they'll get stuck back in here, then it is in a partially loaded or loaded position at that point, which in the field, if you're having to do a repair like that, you always end up having to reach in there with a set of pliers or something and pull that slide back over to you so that you can get to it, service it, and do what you got to do. So coming back to the female unloader, it's at startup that we need it. And one of the symptoms of this failing is we will constantly go into a low suction pressure alarm. And this is where it gets real tricky. This has gotten me a lot of times. These chillers will pump down when they go to turn on. So when they start up, they will be the evaporator is pumped down because they're using a DX style evaporator. So a DX style evaporator means that's direct expansion. Our refrigerant is inside of the tubes. Water is on the outside of the tubes. So with a regular flooded, it's the other way around, where the refrigerant would be on the shell side, water in the tubes. These chillers do a pump down cycle at shutdown of the compressor. That is drawing all of the liquid refrigerant, and the EXV will fully close. So it'll completely close down, isolate the evaporator, and pump it down. That is the shutdown cycle for these. So what'll happen is when that female unloader is either stuck, not working, or is energized when it's not supposed to be, which does happen, the evaporator will pull into a low suction pressure pretty quickly. But then if you if you didn't just accept the alarm for what it was, and customers are really prone to doing this, they'll just go in, they'll try, okay, well, I'm just going to reset it, see if it comes back on the next time. And they do, and it does. The reason it's able to start the next time is because usually the first time it tripped, that EXV does open, and it does get enough refrigerant into the evaporator that once the compressor trips on a safety, it doesn't do another pump down cycle. And once that safety is triggered, it's hit. So the valve will still close, all that process will still happen, but we have an immediate shutdown versus a pump down. What that ends up doing is it puts just enough refrigerant into the evaporator that when you go to try to do the next startup cycle, you end up making it to where the EXV can open fast enough to catch up, even though the compressor is not properly unloaded with the female unloader. So that'll be one way that you can get around that. Now, another symptom would be they stick, instead of sticking in an engaged position where the bypass is closed, they could also stick in an open position, and in that case, you're not able to actually build load on the compressor. So you need the compressor to stage up and to begin pumping more refrigerant and just do its job, and it's not able to do that. And there's a tone difference that you can hear between when the female unloader is engaged and when it's not. Now that takes a trained ear to be able to hear for that and to tell the difference, and it can be really tricky to distinguish that. So even if you have a trained ear, it's not always real quick, but you should be hearing the solenoid's firing sequence as it's going through there. And if you hear that the female unloader has engaged, but you didn't hear a sound change in the tone, or the compressor is just struggling to stage up, while there could be a slide valve issue in your male load and unload valve, those could have an issue. You could have an oil issue. You could also have the female unloader that is not closing the internal bypass. And at that point, the compressor is just not going to be able to increase in its staging. Now, the slide will still technically function, so that part may still be functioning, but you're not going to be able to get to capacity because majority of your discharge gas is just getting routed right back into the suction, and it's just cycling internal to the compressor. There's no actual flow happening, which does cause higher temperatures in the compressor. Like there's a whole rabbit trail of possible symptoms if it was allowed to run like that over an extended period of time. Yeah, great question. Really great question. I do see, so as if the discharge superheat control for the YK using liquid injection, I don't have that sequence to memory. I know that YKs have a liquid injection port that'll pipe into the back of the compressor. It's not something I have seen used as much in the machines I've worked on. I don't have that specific set points and like the sequence of operations for that valve specifically. I don't have that down by memory, so I would have to go back and reference that. So I'm not going to be able to give you a satisfactory answer there. And how you doing, B? Will I ever go back to the field? I don't plan to. Like I do, in terms of doing consultations, right? Consultations, trainings, doing some field training type stuff. Like I've got plans and I still do that. I just had one this week, where I went and did a 2-hour presentation and just kind of talked to a group here in Austin, and it was just an in-person training, right? I do those on occasion, but I don't expect myself to actually go back to the field. You know, I put my time in there. I did those years, and my my purpose and my function is to do this here. Because one of the things that really stands out to me is nobody else is doing it. And somebody has to. Like, we as our industry needs somebody to sit in this chair and have this conversation and to be able to do this. And nobody else is doing it. So in that light, like, this is what I have to do. Now, I enjoy this. Don't get me wrong. I don't want that to come across as though I'm forced into this. I love this job. This is the dream I've built towards. So I have it. And as much as I love the field and I love the hands-on, like, it really does speak to me. That does not beat this for me. And I'd much rather sit here and have this conversation and have the freedom to have this conversation. So yeah, I don't plan to. I do stand. I do see yours, and you're actually you're in the portal. I saw. Yep, I think you are. Is that Echoes? Sorry if I pronounced that wrong. Either way, I'm coming up to your question next there, bud. Line Pride Homestead. Yeah, that's the family channel for those who aren't aware. It's on standby. We've got a lot going on family-wise, a lot. And the academy is requiring a lot of time. We do plan on doing something with the family channel with time. It's just not the time now. When we had to put a pause on it, or I put a pause on it due to just life. So yeah, thanks for asking though. It is something I do think about it. I haven't forgotten about it. Just time. Okay, are you hiring? I will be at some point. I'm gonna need help with this. Like, that is something that's a very real thing. I can't do all of this at the volume I'm doing it forever. Like, I will need assistance. So it's something to just keep in the back of your mind for anybody that might be interested. At some point, I'm not right this minute. Don't get me wrong. I'm not right this minute, but I am definitely going to. Okay, let's get the next question loaded up here. We got the man himself in the chat, Mr. Stand for Justice. Okay, come over here. If I sound like a corny nerd, well, maybe I am. I'll live with it. That picture is throwing me off. I wanted to put it right there, but it's actually over here, edge of the screen. All right. Why don't screw type chillers have receivers built in it, unlike reciprocating or scroll type chillers? So most of the I get the impression that most of the scroll and reciprocating chillers you come across do have liquid line receivers. And that would make me think that you're probably dealing with what I would consider more of like a process, or more like a small process chiller. So those styles are a little bit different than I would consider, say, maybe the larger standard heavy commercial side chiller. So the one here behind me would be an example of a CGAM. So that's a Trane air-cooled scroll. It does not have a liquid line receiver. And I would say that most of that particular sector of chillers typically don't. So when you get into the larger side, these smaller ones that are being used for, say, process chillers, so those are going to be your CT machines, CNC, specialized pieces of equipment, those will typically have, or they may have, a liquid line receiver due to the fluctuations in load. Now, that doesn't mean that there aren't some other specialty built and, say, non-major manufacturer, right? So when I say major manufacturer, I'm thinking of the designs I see from Carrier, Trane, York, and Daikin. Those are the main ones I think of whenever I think of the major brands and how they build it. So you may have something that is not one of those and that is specifically built. I do see that, what is it, some of the heat pump chillers coming out on the market, which this is something I'm looking deeper into and I'm just getting my more familiar with. It's not something I have seen in my local area, but I know that heat pump chillers are really becoming far more popular and they're getting heavily pushed. You see that at AHR shows, where just about every chiller display that's there is a heat pump capable chiller. So let's get into my thoughts on just where the liquid line receiver comes into play in the first place. So the liquid line receiver is there to help give the refrigerant space as the load demands will heavily fluctuate. This is why we see liquid line receivers in like low temp refrigeration. There can be extreme swings from not only box load but seasonal swings where the amount of refrigerant we're needing to push through something can vary heavily. So much so that just stacking it in the condenser, especially if we have a very small condenser, is not sufficient. There's just not enough room to stack that much without causing head pressure issues as well. So in those applications, that liquid line receiver becomes kind of a, call it an expansion tank, okay? So we want to get into, say, if you're comfortable with hydronics terms, that liquid line receiver, I would compare it to like an expansion tank, where it is helping us maintain pressure and store additional water, if you will, for the loop. Now, if you're not comfortable with those either, it's just a type of reservoir, a refrigerant reservoir. Now, why don't, say, standard machines, especially once you get into the screw and centrifugal world, why don't we use that? And I would say it's because of the purpose that they're built for. The loads tend to be far more stable and consistent. We also have the ability to stack the refrigerant sufficiently. So when we are in a lower load scenario, one, we are heavily unloading the compressors. So we have the ability with these types of machines, whether it be through the slide valve on the screw compressor, whether it be a variable speed if we have that, or both in some cases, we have the ability to reduce the compressor capacity itself, which reduces the flow through the machine on its own. That's something that, like with a scroll machine, unless we have multiple compressors, we don't have the ability to do that. And I would venture to say that if I'm right about you're seeing this in more specialty, like process cooling applications, then you're probably only seeing one, maybe large compressor, but just one compressor, and it may or may not really have much in the way of unloading ability. But that is not true when we get into these other types of compressors. We have the ability to unload quite heavily in most cases. So that helps compensate for when we start to reduce load, we have the ability to regulate our flow much better, and we don't need the ability to stack that liquid refrigerant somewhere the same way we do with these other types of systems. So I think that would be the most basic breakdown I would want to give on that, as to why some chillers may use a liquid line receiver versus others don't. It's going to come back to, one, how much can the compressor unload itself to regulate that refrigerant flow so that we can tune the flow to the load. And then two, what kind of swings does that chiller expect to see? Is it going to have to sit in a very unloaded state for an extended period of time, just barely kind of cruising, and then have to scale up very heavily, very fast to capture the load situation? You know, I'd say a CT machine especially might be a prime example of that, or a CNC machine at that. We may not want to shut the chiller down, so we'll let it ride at a minimal load for a while, but then once we fire up an operation, we need to be able to capture all of that electronic load quickly to maintain a stable temperature. Anyway, it's a good question. Very good question. We do have one more in the portal. Let me kind of just skim through some of our chat here. You think HVAC is a good career to get into for someone who has an associate's in electrical tech but wants to work with electrical motors and controls? Absolutely. Yeah, if you're big into electrical, then I mean, I think this is a great career for that. And that's one of the things I love about HVAC as a whole, is we are we're a blend of all the various trades. Like, it's amazing what we get to do between plumbing, electrical, the science aspect of this, dealing with the refrigerants, the hydronic side, which I guess ties into plumbing in many ways, the mechanical aspect, you know, working on a semi-hermetic compressor that we have to tear down, and some of these are literally just a car motor built into a refrigerant compressor, like your Carlisle's as an example. Yeah, it's amazing how much we get to do in one trade, and just the variety and the aspect, and then you throw the controls aspect into that. So what I might say is, if electrical and controls are really your thing, so there are people who specialize in that. You could specialize in motors. So there's every major city that I have seen, there are motor shops in that area that specialize in the electric motors that we use, whether it be from a rewind to servicing. There's some shops that you can pay a little extra and they will come out for you as a contractor, and they'll do the motor install and the alignment, whatever else you need for you, right? You could get involved with one of those companies as an example. There's some of those companies that also do some controls work, or you could just go straight into controls and automation, where you're not even doing anything mechanical if that's really not your thing, and just solely focus on the controls aspect, the automation, where you're building, you're working on data buses, you're building programs and logic, you're still working with all the electronic components, the sensors, and all the schematics that are needed for that, and you're making all these PLCs work together. That's a programmable logic controller. So that's what we refer to those as. You're doing all of that, and it's all just a lot of electrical, very minimal of the rest of it. And that's so all of that's going to be on the commercial side, I will say there. So when we say HVAC, that's an extremely broad category for a very diverse industry, very diverse. You will have varying levels of all of this. So if electrical and like controls and electrical type work is really what you care about, then getting into the heavy commercial specifically side of this industry, which chillers fit into that subcategory of heavy commercial or industrial work, and then even like rack and supermarket systems, from a controls perspective, those require a pretty serious control system to operate those, just like an industrial plant or a regular just heavy commercial building would require as well. Those are areas where you can, if you can move in that direction and specialize in those, you'll get to do that work that you want to do, versus if you try to come in and do that in residential or low temp systems or light commercial, you're going to really struggle to do the kind of work that you want to do, because those require just a bit of a different skill set for the equipment that they're working on, and the the types of customers that are there. So that would be my thoughts on that. And sorry if that turned into way more of an answer than you were seeking. Kind of got off on a spill there. Okay, we've got one more in the portal, and then we'll hone in on the chat. Let me get this loaded up here. That was a bad idea. Okay, we'll go with this. I have a YK with VSD PRV board, displays 5 VDC until you plug in the PRV. It reads 3.3 VDC. I replaced the cable and PRV still won't close after opening during calibration. My thoughts go in two directions. It could either be potentially a board issue, and I don't remember without referencing the manual on that, on exactly what those voltages are supposed to be. The 5 VDC does sound right, but I also know that, so I say that. Yeah, I would need to reference the schematics and what you're actually working on, because I know part of that I think should be a 120 circuit. Part of that should be a 24 volt circuit for the signals. The actuators I think are 120 or 20. Again, I got to look back at the schematics for that specifically, but if you're saying that you've looked at the schematics and you're confident you should be maintaining a 5 VDC, but then it's going to a 3.3 VDC, you've replaced the cable and you've replaced the actuator, it's still not doing what it's supposed to do. My mind goes in two directions. One, the module may be a problem. So see, the PRV, that goes through the I/O board. So you could have a I/O board problem. He said PRV board, which PRV for, let me break down some of these acronyms. VSD, variable speed drive. So that's your variable frequency drive. PRV, pre-rotation vane. So PRV board. The PRV feeds off of the I/O board. So I'm just trying to think to make sure it doesn't come. There's not, because there's different configurations for those OptiView panels. You've got the micro board. You can have an ACC. You can have a stall detector module in there. You have the I/O board. I can't think of a, when you say PRV board, that kind of trips me up a little bit. I'm trying to think of a configuration where the PRV doesn't go through the I/O. Maybe I'm just not aware of it. Either way, so you replace the cable, replace the PRV, still won't close. So yeah, either way, the module itself or the wiring, those would be the two main things I would be worried about. Either, so without a load connected, a module or a board may show full voltage output, and it can show that just fine. But there could still be weak components inside of the module that once you plug the component into it and you put a load on it, now because of the load, it's in the weak circuitry internally, it's not able to properly supply to that component, whatever the component is, in your case a PRV actuator. Unless you mean, I'm getting off on a tangent, unless you mean the PRV sensor, position sensor. Let's see, replace cable and PRV. Still won't, no, you're talking about the actual actuator, yeah. So either way, you put a load to it and now it's going to now it's going to show a lower voltage, which in your case, that would be enough of a voltage drop to not allow it to function properly. Now, if it's not the module, then it could be just an improper wiring. So those actuators, they're pretty intricate in what wires need to land where, and they do change from model to model. So I've found that when I was replacing a older style actuator motor with a newer one on those YKs, that the schematic wasn't a like for like. They were slightly different, and I had to do some work and thinking to make sure I got everything landed where it needed to be. So that is something that could have happened. Maybe there's a wire out of place. Maybe it didn't get wired back just right, or that module seeing that drop could definitely be a problem. Yeah, that would be the two directions I'd want to go. Like, you're confident in the cabling, you're confident in the PRV itself, which I really wonder. Just I'm getting hung up on the way you structured it, whether or not you're talking about the PRV sensor or the PRV actuator. Yeah, because if we're talking about the PRV sensor, the reason that's hanging me up is that 3.3 VDC when it's plugged in, depending on what position the rheostat's in, would be normal, because that rheostat is causing a voltage drop, which correlates to a specific ohm value, which is what the panel is using to confirm position. So yes, the board will show, the module, if it's the PRV sensor, the module will display a 5 VDC signal until you plug the sensor in. And then as you rotate the sensor around and change its resistance value, the VDC reading at the module is also going to change, that's how it's supposed to be. Now that won't affect the actuator itself. So those are two different things. The actuator, and maybe this is where things are getting mixed up for you. The actuator is a separate thing from the sensor and why it's reading that way. And I really don't think that, I don't remember the actuator receiving a 5 VDC signal. That's part of what's got me, hung up, and why I'm really struggling processing the question, because I just don't remember the actuator getting a 5 VDC. I remember getting a 120 and a 24, but I don't remember the 5 VDC signal. But I know that the position sensor does. It gets sent a 5 VDC, which then gets the voltage drop applied to it, and that becomes your position, and that's what we calibrate to. I don't have a concise answer for you, but that's kind of the direction I'd want to go. Hopefully that is usable in any way. I tried. Okay. That's the thing, here, we don't always have to have the answers, and this is something that comes up in conversations when I'm talking with technicians, is it's okay if we end up in a spot where we have to say, I don't know. And I think we should be more comfortable with that than we typically are. It's hard to be comfortable feeling inferior, because you're supposed to be able to answer the question. Like, you're trained, you're the professional, you're supposed to have the experience. And if you can't answer the question, well, maybe you're just an inadequate technician. That's not true, especially when most of us, in my opinion, don't get to specialize in a particular manufacturer, much less a machine. And so, and these machines get so complicated and in-depth that it's not possible, in my opinion, to truly memorize them on that scale, unless that is literally the only model number you work on, especially when you start factoring in revisions and updates to the design, like the vintage itself, well, that means a design change. I don't think we should have such a problem saying, I don't know. And I bring this up because this also came up in the class I did this week. When during the class engagement interaction, it really became a struggle in the beginning because sometimes the answer was, I don't know. And getting the class comfortable with saying that was not easy. I think this is something I want to push more. Like, we don't always have to know the answer as long as we can go find out how to get the answer later, which this is not a format I can't do that here on a live stream, but that is something that we can do. We can go in and look at the information we need to. And I think as a tech in the field, having a broad enough base knowledge of how things work and what should work was what helped me be successful. The other part of that success metric was my ability to use the manufacturer's material and IOMs and what they had, and being able to quickly reference what it shows in their books. And that skill is what created that balance. So sometimes that meant, hey, I need to go verify what the manufacturer says on this. I want to make sure that I'm right. And that's how I would phrase that to the customer. Like, I'm thinking this or something about this doesn't look right to me. I really want to make sure I see what the manufacturer says. Let me take a couple of minutes and go verify this so I give you the right answer. That was my approach I would try to take most of the time. And it worked out fine. Like, I rarely ever had issues with somebody taking that approach. And it's a way of giving them confidence that I'm trying to do the right thing versus I'm just ignorant to what the right thing is. And maybe that's a helpful way of framing that. Anyway, I'll move on. Being a nerd feels like a prerequisite in this. Well, especially if you're going to get into the heavy side, right? And it depends on how successful you want to be, but I will say that having a nerd-like mentality will really help you out in the heavy commercial chiller side. I mean, we just get into so much stuff. Welcome from Saudi Arabia. How you doing, Mr. Shorts? Why IGBT failure? You know what? This is a great time to break out the overhead. 1 second. Because, of course, I have an IGBT. I also have a meter. Yes, I keep these things at my desk. Okay. So let's get the question up here so everybody can see it. We can start from there. All right. So why IGBT failure? Why do they fail? What leads to that? What are some symptoms? Like, what can we do for that process? So let's come over here. This is an IGBT. So let's start with some of the basics. This is a insulated gate bipolar transistor. In short, there's a set of diodes in here that control flow. What this device is doing is we are inputting, make sure I get my orientation right. So this is my DC bus side. So this would be my terminal 1, 2, and 3. And then these two are 1, 2, and 3, 1, 2, and 3. So DC power is coming in from this side, and then I am feeding AC out. Now this is a PWM, so we have our DC bus, and we're going to have, this is going to be our positive and our negative, and then positive and negative, positive and negative. Okay. On the output side is going to be our AC. So all of these are going to feed into the AC. Now, depending on the configuration, this could be a single leg, so we could have L1, L2, L3, or there could be a bus bar across here and making all of this just one leg of power, and then we would have multiples of these modules in there. So this is just one configuration. Another thing to note with these is that we have individual gates. So right there is 3 gates, gate 1, 2, and 3. Now they're combined in a single module, but they are independent gates. They can function in unison, which is part of what the modules is doing, is it's allowing them to work together as one single unit. And we do this to help distribute power flow, because it's much easier to combine a series of smaller gates than it is to make just one big ass gate. It's far less efficient, and from what I understand, it generates a lot more heat. Like I've seen these modules built in a way to where they are one module, and like they're immense. Where these are far easier, I would assume far cheaper too, because you actually can buy these in the individual gates, and they are literally these exact footprints, just one by itself. Anyway, I'm kind of getting off on a little bit of a spill. So these fail for a couple of reasons. One, and this one's less likely, the motor side, which is over here, the motor side could be what failed. The motor failing, causing a overcurrent condition or something here in the bus, or maybe it caused a backfeed for one gate fed into the other gate and it caused an internal failure. Something like that could happen. Does that happen very often? Not in my experience. Usually what I'll see with these is these actually have really good like protection built into most of them. Now this is one of York's versions specifically. This is just a version. Another way to call an IGBT is an inverter. So if we start talking turbo cores have an IGBT in them. It's what we just call it an inverter. This is an inverter. It's just another way of saying the same thing depending on who you ask. Anyway, these have good protection in them most of the time. So I don't see as many output failures or even input failures in some cases. I don't see as many because the module will detect a problem pretty quickly and just stop everything before a complete explosion happens. So in my experience, one of the more common failures I'll see is either it'll be heat related, where the cooling system, which is what this is down here, these are plates. When these are in operation, these generate a lot of heat. That heat is just waste energy that is just natural to using solid state components. We haven't developed technology to avoid that yet. It just kind of is what it is. So we have to reject that heat somewhere. This particular one would have used a liquid cooling system. Some systems will use a air-cooled system to cool a heat sink. Just those variations will vary. But the point is, overheating is one of the symptoms that I see. They'll run hot. Now these have temperature sensors in them, but these temp sensors are only set to be a safety metric. And you can run really high temperatures on these, and those high temps are really hard on the silicon. So there's a difference between silicone and silicon. Silicon is the base element that all of these things are made out of. Silicone is a product that we use for sealing purposes, and from what I understand, it is made out of a silicon base material that's turned into a dryable gel, if I'm not mistaken on that. Either way, with these, the way that I've been taught is these are like fibers inside of here. So we move this to the side. If we have one gate, okay, inside of that gate has a series of call it like fibrous material, and that is the silicon material itself. Now, in reality, we've got diodes and stuff in there that are preventing flow, and we're doing different things. I could get into this on a schematic level, but we'll save that for another time. These fibers, which make up our internal components, our diodes, they don't like heat. Heat will make them break down, which is why in some cases things will work just fine when they're cold, but once they start to warm up from operation, then they'll start showing symptoms. So when this base plate isn't being regulated at a cooler temperature than it probably should be, even if it's below the alarm threshold, that creates extra stress on those fibers, and those fibers will have a shorter lifespan. They'll break down faster, and they're not going to be able to carry that current load as efficiently. So what that ends up leading to is you start having an actual gate failure, where the gates themselves begin to just not process properly through them. One of the common signs I'll see of that is, one, you could have a motor current issue where you have motor current alarms. That could be because one of these gates is not outputting correctly. Another could be almost a grinding noise. So I've had it to where the compressor will sound like it has a bad bearing, when in reality it's not a bad bearing. It's the IGBT. And what I find is the IGBT is outputting a very dirty AC sine wave. And because of that, and because it's not synced up properly, because one of our gates is having a problem, it creates this unstable field on the motor. And that unstable field ends up causing a vibration, which sounds like a bearing problem, but it's not. It's not. You can go put a new set of gates in, new set of IGBTs in, and it'll clean up and it'll sound just fine after that. It won't have a problem. That is a prime example of where you had a weak gate and it was causing a harmonic vibration on the motor itself. Another way I've tested this is if I've had a system where I had multiple compressors, I would actually sometimes swap the gates out. So, or if I had multiple chillers there, like if I really thought this was the case and the customer wanted to for sure know, not just go off of my best assumption, then I would take one of the other IGBTs, put it in its place, and we would run test it and see if the compressor sounded better. If it did, we knew for a fact that that IGBT or that inverter needed to be taken care of. One of the ways to test this is with your meter on diode. So that's going to be this little setting right here. We can measure across these. Now, this being my terminal 1, everything's going to come back to here. And I'll make sure when you're doing stuff like this, make sure you're testing the actual pads, which is this part, not the threads. If I reach down in here and these threads aren't making contact with the pad, it's going to give me a different reading, or it could be a false reading. So make sure you're making contact with the pad. We see OL, we see a 0.34. Now for this particular one, that's a good reading. And that's what I would expect to see. And it doesn't matter which of these other pads I go to, I get the same thing. That's because both of these are the same output internally, and then these are two separate inputs feeding off of the DC bus. That is how we're able to create the AC sine wave, is by manipulating this positive and negative DC input. Anyway, we flip the leads around, and now we're getting different readings. So you could have a scenario where in the field, this test right here, this IGBT just passed. Right there, this just passed. Okay, now I could do the other 3 gates. But let's just say all 3 of these pass, but I could still be having a vibration issue from it. And that is because these gates haven't outright failed, but the fibers are still weak. So without a load, like I'm not putting a load on it with this. This is only just testing the circuit electrically, but it is not putting a load on it. So when the load is applied to this silicon, you can still have symptoms of a bad IGBT that you can't measure. So it's just something to be aware of it when you're going through the process. And again, the question was, why do they fail? So the heat, the silicon breaks down. You could have any one of these little module components fail. These plugs that go into them, these are common failure points we struggle with. So you could have a bad plug issue. Taking a little control screwdriver, which I don't have mine close by. It's in my tool bag out in the shop. Even if you use your meter lead, like when the plug's in there, actually making sure that each of those pins are fully depressed, that's an important troubleshooting step, because that can cause instability here, because these three gates have to work in sequence, whether they're individual legs or whether they're one common leg. They have to work in sequence with each other. To get that sequence perfect, we have to make sure we have solid connection here. So that's where this Molex point becomes an extremely common failure point, because we don't have a solid enough connection to properly control these three modules in sequence with one another. So yeah, I'm thinking through just all the different ways that these can have a failure. So heat, you can have a DC bus voltage is just wrong coming in. You could have too high of a DC bus, too low of a DC bus. Those will typically trigger alarms. You could have a motor failure or a short to ground, something like that. That could cause an issue here potentially. But the most common I see has to come back to whether it be a cooling issue or just the silicon broke down with time, which even if the temperatures were maintained perfectly, that's just going to happen. That is a failure point of these. This silicon will break down, will begin to have issues, and eventually just fail. There's no way to avoid that. There's nothing we can do to prevent that from happening. So at that point, we just have to diagnose it and replace it. It's just like a lot of other things. These components aren't built to last absolutely forever. So they're going to have failure points. Just the condenser fan motor, bearings, all of these are components that fail with wear and tear. The silicon components are no different. Absolutely no different. So it doesn't mean that there was a source of cause for the failure versus it could have just aged and wore out. I mean, think about the current draw we're putting through these things. And we're moving major amounts of electricity through one of these modules every day, all day. It's a lot. It's a lot for these to manage. So, yeah. That would be my personal breakdown or explanation of why IGBTs fail the way they do. Some things I would add to that. Keep in mind, IGBTs can be used as both an inverter and a rectifier. So in a lot of drive technology, like variable speed drives, we have historically used SCRs as silicon controlled rectifiers, hence the rectification. So we've used those rectifiers to be our rectification circuit to get our positive and negative DC bus. And if I'm not careful, if somebody wants to dive into this on a deeper scale, you're more than welcome to ask the question. I can do a whole bit on just VFDs, VSD theory in general, and I can talk it out here. But we've used the SCRs to do a rectification, but and a lot of, especially with York, I see them moving to using an IGBT as the rectifier and the inverter. So the inverter and rectifier indicate its actual purpose in the system. The IGBT or SCR is the style of component that is being used. What is the internal makeup of the silicon that we can expect to see with a component like that, versus what role it serves. So the inverter and rectifier is the role. The IGBT and SCR is the type of component itself. That is one way to distinguish those. Yeah, so just be aware. IGBTs are being used in more than just inverter scenarios. I do not see SCRs getting implemented as inverters, but from the way I understand it, I don't think that's possible. An SCR cannot be applied as an inverter the way that an IGBT can, because of the internal gates structure that they have. They're just different. Great question, though. I'll try to get more. This stream, like, I've got a handful of things kind of floating around, but I just wanted to kind of test this whole idea to begin with and format, which so far I think it's going pretty well. So I can get more. I've got a whole bunch of stuff I kept over the years that I can use for this. I'll try to do that. Okay. Questions. Thanks for clear. Each one is unique. That's what tech support is for. Problem is it's almost impossible to talk to. Yeah, right. That is a major problem we've had for a lot of years, and it's only getting worse, in my opinion, for tech support in the industry. It's just not there. And the manufacturers have lost a lot of their incentives to support it because they want to make more money, which means they can either sell more equipment, which they're trying to. They can also force companies to use them as their contractor, which is, they've been extremely aggressive in the local Central Texas region, especially, which I think the growth we've had here probably may have a lot to do with that. They want to be on the front of that growth and capture all that market share while it's growing. So that's a fair, I mean, it's business as far as they're concerned. They're major corporations. It's just business for them. I do know that Carrier does still have some level of call-in support. Daikin has some level of call-in support. Depending on what you're working on, though, like I know Daikin especially, you have to be certified in that model to get to their support. So you can only get so far into it before, if you don't have your certification number to back up who you're trying to get in touch with, they won't actually let you through sometimes. So those two are probably still giving us the most support, but there's still barriers as to what kind of support they'll offer. Joe Tech from Chicago. With all the new control systems and technology that are manufacturer specific, constant education and training are paramount, especially with warranty processes now. Absolutely. Yeah. I mean, it really is. And it's hard to keep up with, especially when so much of it so frequently changes. But that is one thing. So here's one point I want to make to that. And it's why I've taken the strategy I've taken with chilleracademy.com. All of these systems are using the same basic principles, using the same basic theories as a foundation to build from. And then they're putting their own tweaks and whatever they want to it. So they are, one of my goals is to actually, and I'm not trying to replace manufacturer training, but I am trying to help you build a foundation alongside the manufacturer training. because what I find is the manufacturer training does not do a good job, in my opinion, in building adequate foundations to do what we do. But they are the best ones to teach the specifics of how their machine functions. Now, you could argue that in some cases, but for the most part, like they can do a good job teaching and training on their machine. So my focus is, let's create a system where we can effectively give everybody the information and the foundations they need to do really good jobs on a general scale, on a basic scale, on the same foundations that everything else is built on. Because there's going to be a lot of things where you don't actually need necessarily the manufacturer to spell this out for you. You just need a basic understanding of what's going on here, and then you can make a successful determination from there and move in the right direction, which is not something you'd be able to do unless you have that foundation in the first place. That is the core theos behind chilleracademy.com and what we're trying to accomplish. And then you add to that the need to keep up with manufacturers' changes. Part of what I'm arguing for is if you have the right understanding of what these systems are doing and how they all are built to work from the ground up, then these constant changes in what the manufacturer is doing will have far less impact on your ability to keep up, because you still share the same foundation that the manufacturer is using to build theirs to begin with. All right, I have a Trane RTUD with a remote air-cooled, I think that's where the RTUD, the remote air-cooled condenser. With wintertime, the chiller seems that the evaporator liquid level is above the point where it thinks there is liquid. I believe that the oil is migrating through the ball check valves, so the BMS does not. When you said winter time, so that tells me that you've probably got, you're probably dropping your condenser pressure. Let me finish reading your thing. It can't be liquid refrigerant because the chiller barrel is 75, 80 degrees because it's inside the mechanical room. And the pressure is at the point where the chiller shuts off after a pump down. Can't be the liquid refrigerant. Right. Okay. Yeah. Which, if you don't have liquid refrigerant in the evaporator, you're probably not going to deal with migration, like 10 or something. I can't remember exact pressure. Has to be checked for accuracy. I did check it. Okay. All right. Yeah. This is a good conversation. Let's get into this. Let me get it pulled up here. All right, Mr. Colin. Pressure, yeah, we'll go with this. This will be enough to help everybody keep up. Okay. I have a Trane RTUD with a remote air-cooled condenser. In the wintertime, the chiller sees that the evaporator liquid level is above the point where it thinks there is liquid refrigerant in the evap. So it is above the point where it thinks there is. Look, so as in, one thing I do want to clarify, chiller sees that the evaporator liquid level is above the point where it thinks there is. So it is seeing, as in at the time of pump down it's seeing this, or it is seeing a high liquid refrigerant level and is trying to control based off of that high level? Because these machines do have trouble where when they do start oil stacking in the evaporator, it will, especially on the older style sensors. I know they changed the style of sensor to address this, but the older sensors really struggled with being affected by the foaming that happens with the additional oil charge in the evap. So the chiller is pumping down because of low ambient temps to move the refrigerant out of the evap. Yeah. So I get that it's pumping down. I'm trying to understand, and it sees the high refrigerant level after. Okay, so it's okay. All right, now I'm on the same page. So after the pump down cycle, it's seeing high refrigerant levels. I would say that if the sensor itself is not sticking, then it is likely due to oil migration issues. You could have a volume of oil stacking in the evaporator, especially like as part of operation and as part of pump down. That oil is going to really get disturbed, and in the process of it getting disturbed, it's going to cause a lot of foaming. And especially with the old liquid level sensors Trane was using, they're very susceptible to foam on the evaporator. And that foam will register a refrigerant level higher than the actual liquid refrigerant level is, as one of the issues that those have had. Again, Trane's newer sensors, which are not the float style, they're an actual an actual solid state board that goes in to monitor the what is it, refrigerant through the continuity as it moves up and down. Same basic thing that YKs are using for their condenser liquid level. Either way, those are less susceptible, and I say less. I'm not going to say that they're not at all. They're less susceptible to that oil charge in there. Now, I think the bigger thing is addressing why the oil is there, and I think that kind of goes back to some adding more to your point on maybe you think that the check valve on the gas pump is having an issue. That could be a symptom, and that is something to verify for. You can see, does the check valve, like with the machine off, you can take a magnet and kind of see, can you get the check valve to move? That's not really going to tell you if it's leaking by or not. One of the ways I look for if that check valve is leaking is when it does engage the gas pump. Do I see a sudden spike in suction pressure and discharge superheat? Like which discharge superheat may be a little less useful, but especially the suction pressure. Like, is there a sudden spike in that pressure? And if there is, then that's where I'm looking at the that check valve to see, okay, is that check valve having an issue? I think one of the keys here is you have a low ambient condition. And if memory serves, you should have now you're going to have condenser fans that cycle based off of saturation, but I think there should also be a pressure regulating valve as well on the bypassing the hot gas to liquid line. If I'm not mistaken, that should also be part of that remote condenser assembly, more than just condenser fan control, because you get into a really low ambient condition, even with the fans off, you can still end up in a spot where the saturation is dropping too much. So, or the pressure is dropping too much on the liquid. Part of what that's going to do is that is reducing your velocity through the system. So if you are not keeping that head pressure, if that PRV is not calibrated properly, and your condenser pressure is able to drop too much in low ambient conditions, you're not going to maintain good velocity through the system and a higher differential. Part of what that system needs to function really well is we need a little bit of a higher differential to push into that gas pump and force all of that that oil latent refrigerant back up to the compressor oil recovery line. So these things have to work in unison together, which means we have to maintain enough pressure and velocity on the condenser side itself. And if we do not do that, it could have issues doing the oil recovery process. So we need to make sure that you're maintaining condenser pressures. Again, that check valve could be an issue. Maybe it's a combination of problems. Maybe that check valve is having a minor issue. Maybe you are having a low condenser head pressure problem. These things could be working in unison. Some of the, let's see, that oil return line should also have a filter on it. You need to make sure that filter is allowing proper flow and it's not needing to be serviced. When was the last time it was serviced? So that would be another possibility if we're making the thought that we are seeing oil and oil foaming causing a higher liquid level being sensed at the point of pump down. So that would be what I'm trying to verify, because yes, it does. I would say that it is likely that could be an oil migration issue. It's also likely, so keep this in mind, that if you're having a heavy oil migration problem and that oil is having trouble stacking in the evaporator and it's not recovering that oil correctly, one reason the liquid level sensor may still be showing level and that it didn't fully pump down is because you hit the pump down set point too quickly due to the heavy oil charge. So that heavy oil charge was causing your suction pressure to dip faster than it was supposed to, which made you hit set point prematurely, and you do actually still have some liquid level holding in there in addition to the oil level. That could also be true, which does still come back to the core problem being the oil. So even if the sensor is not getting a false reading from the oil, let's just say that sensor had a good reading and it was actually reading refrigerant. Let's go that path. Then that would mean that it is because of the oil, I would say, because of that oil stacking in there. And being that you're seeing this on both sides, I think you said it's happening on both circuits. It's happening, both circuits. So the chiller is pumping down because of low ambient. Yeah. So the same conditions happening on both of your circuits, which takes me back to how we're controlling head pressure. And I think that's the big thing. You're only dealing with this at low ambient conditions, which that's where I come back to, okay, well, are we controlling head pressure properly? Because even with a gas pump, with eductors, it's necessary for the Venturi effect to maintain a higher condenser or high enough condenser pressure to get a siphoning effect through our eductor. So that's necessary. Well, these gas pumps aren't using a Venturi effect, but they are still needing a sufficient amount of differential to be able to push that oil latent refrigerant back up into the compressor to get that oil recycled into the system. So that, again, I don't think it's coincidence that this is a low ambient problem. But I think that would be a reasonable explanation as to how to explain the condition, why the liquid levels are showing higher. when it is having a problem. That would make sense to me as to what I might expect to see. But I think that is a symptom of the oil issue, which the oil issue may be a symptom of head pressure control problems. I'd be curious to your thoughts on that, or if anybody has any additional thoughts on that. If me being on site though, that would be the road. Like that's the road I'd be chasing down personally. Which, if I had to give a number, I would say I would want to maintain a head pressure of at least 70 to 75 saturation on the condenser, at least. And if I was pushing down to that or below, especially below, then that's when I'd really start thinking, okay, well then this is for sure part of that problem. I'm trying to think though, because I don't remember. I know with a CVH, you can push those to about 70 degrees before that eductor starts having problems on the condenser saturation. I wonder if the RTHD, especially with a remote condenser, because you're also going to have some pressure drop and stuff too to factor in. I wonder if those, or I said RTUD, sorry. I wonder if those would I wonder if they need maybe a slightly higher condenser saturation. Maybe 70 degrees may be too much for those. So maybe running closer to 80 would be better. And that could be a situational thing. That's the thing with remote condensers. That's a field installed aspect. That's no longer even an engineered part of the system. So we do have to do some additional field calibrating to account for whatever added line length and everything else that happens in addition to that. So it may be that other RTUDs may run at that lower saturation just fine, but it's possible that with your configuration, you may need a little bit of a higher saturation set point to still safely function. And that's where this conversation comes in, and our skill as a technician kicks in. So the BMS short cycling the chiller could contribute to this because the BMS often shuts down the chiller when it's running full out. Short cycling, yes. If it is not, because that oil return system needs time and operating time in order to function. And so if we're giving that chiller like short spurts of run, and I say short spurts, I mean we're talking less than an hour. If it's having to do a startup and it's getting an hour or less of runtime and then shutting back down, then you do that often enough, yeah, you probably would have more migration issues. If it's able to run for a few hours at a time with each startup, as long as the rest of the system is properly working, I would my assumption would be that would be enough operating time to recover the oil as needed. And then it's going to go through its normal pump down procedure, so all that should be fine. So then it's just a matter of how do we get back. You said they run 5 to 15 minutes. They're having that thing turn on for 5 to 15 minutes. No. Is the short answer. No, that's not going to work. Not at all. That's just not enough runtime. That is not enough operating time to allow that oil return circuit to do its job. Like that's that. Okay, so at that point, then it's a runtime issue. Absolutely. You're gonna lose a portion of your oil at startup regardless. Like just as part of the compressor turning on and coming into operation, you're gonna lose a part of that just from that process alone. It's not a major amount, But you do this enough times over a span of time, you will start to migrate just from the constant starting. And then yeah, these things need 30 minutes to an hour to run enough oil recovery cycles to properly manage that oil return circuit. If it has less than that, it just doesn't have enough time to, because you got to think, there, let's come to the whiteboard. This is our evaporator, right? And then we've got our gas pump down here. We've got one line coming up to our compressor up here. Okay, so this is our return line coming up and into the recovery port. We've got our drain line, and depending on your system, let's say you have an older one where we've got, as I learned recently, the newer ones don't have this vent line anymore. Either way, whether you do or don't have the vent line, that's irrelevant. And then we've got our hot gas. Get that off of there. We have our hot gas coming over and pumping in to push all that back out. And right here is your check valve. So we've got to give this system enough time to drain down. So we have a liquid refrigerant on a falling film evaporator. So we've got a very low evaporator level at that. There's a lot of refrigerant sitting in there that this has to drain down into. And if I'm not mistaken, I could be wrong with this, but removing this vent line, if you do have a machine that did remove that, that does slow down this process, to my understanding, because we now have to basically kind of gurgle, if you will, back up into the refrigerant charge, right? So we've got to work the liquid refrigerant draining down into whatever gas is in this chamber. Either way, I don't want to speak out of turn there because I'm not as confident with that. Regardless, it takes time for this liquid refrigerant to drain into this chamber. And if this can't happen fast enough, or it's not going to happen that fast, is what I'm trying to say. Because we've got to fill this chamber, and this is on a time cycle, and this takes, I'd have to look at the books, but I mean, it's it's several minutes per cycle. Minutes per cycle. That is just one. And you got to think, a small volume of oil is actually getting captured into this chamber compared to what is stacking in the evaporator. And we need to get several cycles through, like a lot of cycles have to process through this pump in order to get the oil charge that's going to stack in here, even just from the startup process, back up to the compressor to return back into the oil separators to recycle back into the oil circuit. And then just basic operation beyond just beyond just startup is going to allow oil to get into here. Like, those oil separators are not foolproof. They do not completely remove that oil. You still have some oil that makes it up through the condensers and back into the evaporator. That is unavoidable. It's why we need this system. 15 minutes ain't going to cut it. Like, not even kinda. 15 minutes is not going to cut it. You take it even less than that. Yeah, so that completely explains your symptoms entirely. Having such a short run cycle, you will start to stack more and more liquid refrigerant into the evaporator that you're not giving the recovery circuit enough time to return that oil back. And because of that, it will just continuously stack and then cause the migration symptoms you're dealing with. Now, everything else we've talked about in terms of head pressure and all the other stuff, that will play a part. Those things need to be dialed in as well, but we have to give it runtime. So maybe, so one of the things you can do, I don't know if sharing this with them would benefit you in any way versus trying to explain it to them. It might be easier just to explain it to them. But I know that when you share a video from YouTube, you can share it with a timestamp. So you could go back to the point they need to hear from this breakdown if you want to do it that way. And you have to click a button, if I'm not mistaken, to timestamp the link. That way, whenever they pull it up, it'll, instead of them having to go through the whole stream or them having to manually get to this point, when they click on the link you share to them, it will take them straight to this to the point in the breakdown that you need them to see. So I would suggest, like, if that will help you communicate what you need and let me kind of help advocate in this way, that's something I would point you in the direction of. And that's something that I've done a few times, even for myself. Like, hey, right here, this point in the video, take this timestamp. This is what I'm trying to say. All right. Well, I'm glad we got to the bottom of that. We can all sleep better tonight. Can't talk to Daikin unless you've been factory trained. Yeah, well, it depends. It depends on which group in Daikin you're talking to. I know for sure on the larger side, that is absolutely, like, if you get into the centrifugal side, and I think even the screw side, you're absolutely right. If you don't have the certification number that they give you at the class, then they won't talk to you directly about it, and it has to be renewed every so often. Like, those certifications are only good for like 3 to 5 years, something like, I think it's 3 years, which York does the same basic process. You have to renew it every 3 years. So, but I think on some of their other, like, smaller systems, if I'm not mistaken, they will provide some level of support. I could be wrong on that. Things do shift and change, and regional also has an impact. Getting to work with everybody through Chiller Academy, I've learned how much, from a regional perspective, even within the United States, there can be major differences in how the manufacturers are supporting that region that's not even national, much less international, or the same rules, I should say. I've heard that about Arctic Cool. Yeah, I've heard that about Arctic Cool, where they've got some pretty good support. All right. Adam, are you only teaching online? Would I say only? No. I commit almost all of my time at this point to supporting the academy and everybody in it. I am actively working on many projects to improve the academy, improve the current training and stuff, but I'm very happy with where it's at. Like, I feel very confident with the material that's in there, and I've gotten enough feedback from it. Like, it is, like, if you really need help with working on chillers, especially if you're newer to this, like, I've worked it out. The certification program in its entirety, it only actually takes about 8 minutes a day of just logging in and kind of going through the material. And if you could spend 8 to 10 minutes at a time, but 8 minutes, like, is actually the hard math on that, and that's actually rounding up at that. If you can do that on a daily, you can successfully work through the certification program. And that program will give you a foundation that you need to where you'll be solid for your career. So this is what I'm doing. Like, I'm putting time into that now, but I have ideas on how to make that better, how to make it more fun and engaging and entertaining, how to make, like, I've been studying psychology on how we learn and how we build the memory structures we have. So in that process, it's helping me see, okay, how can I make this resource better so that you can maximize your time? Because if I can build it in a way that works naturally with your brain, and helping your brain build memory structures, then every minute you put into it, you get more out of it, strictly because I learned how to do it better. So that's really what I'm doing at this point. I do some consulting, I do some in-person training, but I do very little of that at this point, because like the academy is it for me. This is what I'm going to be doing, and all of my resources are completely devoted to that. Everything I've got going. So I do. So the technical answer is, do I do more than online? Yes, but not much. Yeah, not much. Let's see. YVAA suction limiting on both circuits at 28 psig. Condenser feeder 37% open. Which I recently learned, or was realized, maybe a better way to say that. YVAA is controlling the condenser based off of subcooling, which is different from the YCIV. It's interesting how much they changed between the YCIV and the YVAA. You wouldn't think so, but they're actually quite different in terms of machine. Let's talk about this. So I am still brushing up on my YVAA. I've actually got the manual. Let me show you. So what I do for my reading, I've got a little iPad mini, and I use Google Play Books because it syncs to my tablet, my phone, or even my computer. But it's actually what I've been reading recently. I've actually been going back through the YVAA manual, and so yeah, I personally have built a habit where I spend less time scrolling social media and whatnot, and I focus more on, why don't I take some time, read up, brush up, let me try to stay as sharp as I can on all these things, so that in the moment, like, I can give you better answers, right? That's my focus. So in that process, I realized just how much different the YVAA is compared to the YCIV. That was the whole point of that side trail. Sorry, that ADHD kicked in for a minute there. Okay. So YVAA suction limiting on both circuits at 28 psig, condenser feeder 37% open. My thoughts on that, because it is both circuits, and it's usually both circuits don't, like, if you had a low charge, for example, both circuits rarely leak at the exact same rate, and these are independent circuits with these machines. They do not share, they share the same evaporator, but everything else is completely independent. So being that they're both operating identically, I would say that it's probably not a refrigerant issue, because with the YVAA, the feed valve is opening and closing based off of subcooling off of the condenser. So technically, if you start to have a low charge scenario, the feed valve will limit how much it's feeding off of the condenser to keep subcooling up, which will starve the evaporator. That's my understanding so far. I am actively rereading that just to make sure I've got all that straight in my mind. But that's my understanding. So if you had a low charge scenario, that could be a symptom, is a low or suction limiting condition. Now, that doesn't sound like that's, obviously with both circuits, I doubt that is true. So what is probably more likely is a flow issue. How about this? We could list out suction limiting potentials. So one would be low charge, okay, which we talked about. We could have a oil stacking issue, which gets us into the eductor problems, or we could have a flow, which I think may be more likely, or heat exchange problem of some kind. So oil stacking is going to create a heat exchange problem as well as flow. So the charge, like I said, with the condenser valve, being that it's both circuits, it's not, I wouldn't think this was as likely. And in this, you're probably going to see that that evaporator sight glass is low. So if you have your sight glass on each circuit, most of the time there's somewhere between, say, a half to about a third, I would say, is normal. And then if you get down below that, or just completely, like, not even in the sight glass in some cases, that's where you're going to see a problem. So my gut would tell me that I would expect to see, with a suction limiting, low liquid level. And this might be what helps me determine between oil stacking or flow. If this liquid level in here is still up in this zone, even though I've got suction limiting, I'm probably going to really start looking at the oil stacking far more heavily. Because at that point, then this oil is getting stuck in the evaporator and it's causing a heat exchange problem, which is causing my suction limiting. Now, you said it's both circuits, so the likelihood that that was identical on both circuits, I would say, is less likely. Yeah, I would just say that's less likely for them to be that precise. Now, one thing to keep in mind is the both compressors run at the same speed. So one of the things that gets tricky with these systems is they share the same drive assembly. So we have our chiller control panel. We have comp 1 and comp 2. These will stage and cycle at the same speed. So in some scenarios, a problem on 1 can cause some weird conditions on 2 that would make you think they're correlated. That's the word I'm looking for. Because they share the same drive, and compressor 2 can't run independent of compressor 1 on the speed aspect. So be careful of that process. We don't want to get in a spot where we think it's both circuits, but it's really one. Now, I would assume in this case you're actually seeing the alarm on both circuits. So both circuits are giving you that low suction limiting alarm. Now, if we were having a oil stacking issue based off of the sight glass, I would really want to go through that eductor system. We need to make sure that the filter dryer is in good condition. It's not causing a pressure drop scenario, and we need to make sure that we've got sufficient head pressure, condenser pressure pushing into the eductor. That has everything to do with how well that eductor functions. So if we have really low ambient conditions and our condenser fans are not staging properly for any reason, that's going to affect how well our eductor can function, which the condenser fans on this machine are going to be variable speed. Each over here by the compressor, there is your drive cabinet on either side for your condenser fans. So you still have the contactors up here in the corner, but these contactors are basically like these are hard contacts to open power to the condenser fan drives, and then the condenser fan drives are what's actually feeding the fan decks themselves. So again, if you're having a head pressure issue, that's going to influence the eductors and your ability to return oil. So more than likely, though, I would really want to blame the eductor dryer or a overcharge of oil. If for some reason somebody added an excessive amount of oil to the system, that's going to cause similar stacking issues because we have more oil flowing through the circuit than we were actually designed to be able to recover at a given time. That takes us to flow. It is far more likely, given what you've explained, that we don't have proper flow. And if memory serves, I'm pretty sure there's actually flow charts in this manual. Now, you may not have this manual. When I was reading through the table of contents, I'm quite confident. Technical data. Evaporator pressure drop is page 101. So let's go look at that real quick. Let's go to 101. Right about there. This is 103. 101. Here we go. Okay, so evaporator pressure drop is designed in accordance with the normal water evaporator condenser flow rates, permitted water velocities, heat exchange between 3 feet per second and 12 feet per second. 2 pass are limited to 45 feet of head water pressure drop. 3 pass are 65 flow. And then these are drops based off of if you have a brine solution. So we don't have an actual chart. What we have is a flow. So in the heat exchanger tubes, between 3 feet per, which is just the velocity, and 12. So 3 and 12 feet per second. That doesn't do much for me, but 2 are limited to. So 45. We're going to multiply 45 by, no, divide 45 by 2.31. Get a calculator going. I never even considered pulling my tablet into this. This just kind of popped in my head as I got it going here. So we're gonna work through this live, okay? We're just having fun today. I'm experimenting. So we got 45 times, divided by 2.31. You could also, there's the 0.433 is another. So that would be, 19.4 PSID. 2 pass are limited to a maximum of 19.4. So basically 19.5 rounding up. Excessive flow above the max GPM may damage evaporator. See table on page 7 for standard 2 pass to determine. Okay, page 107. Dimensions, here we go. Okay, so on this page, we can get into our model. And then these are our frames with our flow rates. Okay, so I hate it when they do this. We get into flow rates instead of actually giving us a DP. Okay, well, at least we do have a way of determine. So this is the chart you basically need to, if we're going to verify flow, we can base it off of this. I would say that these larger ones up here at the bottom of the chart, which can handle up to almost 1,600 gallons per minute, that's going to be your maximum of 19.5 PSID based off of that evaporator design. So that would be my expectation for that. In terms of flow is very likely going to be probably the most probable cause here. Is the baseline I'm getting to. I don't know that you have enough flow. Too little flow. You don't have enough heat getting into the evaporator, and that is causing a suction limiting problem. And if we increase the flow after we've verified the rest of this, I would expect to see these conditions improve. Now you might say, okay, well, flow hasn't changed. So we're running the same flow that we've had for forever. That may be true, that may not be. If that's an assumption, I would say don't. I would challenge the assumption. Let's actually dive in and go look and see. Did a strainer plug up? Did something happen? Do we have a problem with the pump? If the let's see. Yeah, I really want to verify the flow. In terms of the oil stacking is something to it would be an easy check to verify, because with the evaporator suction limiting, we should see a very low level in the sight glass. And if we don't, then my mind goes to, okay, well, then I've probably got an oil migration issue. Let's address that issue. If we're bad enough in the evaporator, but we still have good oil levels in the separator, you probably overcharged on oil. And that, if that was done to both circuits for some reason, then that could explain why they both look the same. You could also have it to where, because they share the same output drive, or not same output, but they share the same VSD in the cabinet, that's going to make them run in sequence. And so you could have some, say, conditions that look the same between the two of them. That's another thing to keep in mind and take it into account. So that's really what I'd be kind of going through at this point, verifying, and then considering the flow, the GPM problem from there. And what do we need to do to address that GPM issue? Because my gut says it's probably evaporator flow. You've probably got a flow problem on the evaporator, and it's causing both circuits to respond the way they are, being that they're that consistent. Because technically, charge and oil migration, I wouldn't expect to be that perfectly aligned, but they could be. So we have to be very careful with the assumptions that we make at any given time. All right, Colin, just wondering, who does your BMS? Never gotten past their phone screener because I asked if I have factory training. I say no. They tell me, sorry, can't help it. Huh. Interesting. Well, that's unfortunate. Thankfully, we do have a friend. We could phone a friend. I don't see him in the chat today, though. Tell him to keep it status enable, local set point to do its own control. I mean, well, the issue with that, Tom, is depending on the site. Like if they're running that short of a cycle, that would tell me that they're probably doing a processing run. So this is some kind of facility where they're doing batches of something, and so they're trying to energy optimize, and they're wanting to shut the chiller off in between batches instead of allowing it to maintain stable operation. And they just only need it to come on for 15 minutes at a time for that particular batch run issue, whatever the heck there is they're trying to accomplish. That would be my assumption. If that is not true, and this is for comfort cooling in some way, and they think that cycling the compressor is somehow improving efficiency, they don't understand basic electric, with a oh shoot, I would blank on this. I was just talking about this the other day. Not resistive load, but oh man, hard blank. Motors change in load based off of how much load you apply to them, where resistive loads do not. And I am completely drawing a blank on the technical term there. Dadgummit. That's going to bother me. I'll look it up. I need to go remember. Either way, yeah, that would be my assumption, Tom, is this is some kind of process. And if not, then they're showing their lack of education, because you don't do that with motors. You want to keep them, especially with compressors, you want to keep them online. That is more efficient to let them run than have them do a inductive. Thank you. Inductive loads. That's the word. It's far cheaper with inductive loads to allow them to stay online than it is to have them constantly have to turn off and on based off of them being an inductive load to begin with. They vary heavily and they require a lot of energy to get rolling versus a small amount of energy to stay online once they are, compared to getting turned on. Yeah, they usually too many hands in the cookie jar. Yeah. Flow, make a valve. All right, we do need to wrap up here. They are basically taking the open percentage of the cooling tower coil valves of the air handlers and averaging it, and when they get to a certain point, they enable the chiller plant. So this is comfort cooling, first of all. Second of all, they're basing it, so that's a load calculation. They're trying to do a load calculation of, okay, well, if our valves are lower than X average percentage, then we do not have enough load to bring a chiller online. And if that, so here's the thing to that. You've got to have some kind of corrective factor there. If conditions are outside of this, or if we are going to have to cycle beyond that, like there's got to be a corrective factor. Like, oh, that's bad programming. Because if you were to chart this, like if the facility was to take their energy usage and chart this out and compare the two, let's just let the chiller stay online at a minimum state for all that time versus let's let it turn on for 15 minutes. That electric usage is going to be substantially higher, because every time they got to turn both of those compressors on, because I mean the chiller turning on at that point, it's going to be seeing water in the 50s, so it's going to want to stage up to a high load thinking it has a hot pull down to do. In reality, it's a warm loop with a light load, and it's just having to they're doing a weird control sequence trying to base it off of load. It's fine if they want to do that early in the mornings when they're still unoccupied, and then not let the chillers turn on until the load reaches past a certain, call it, staging point. But they can't leave it like that long term. Like, they have to, again, the corrective factor has to be there to adjust for that. There's other ways of doing that doesn't short cycle the chiller. But I would put money down that they're trying to energy optimize, and that energy optimization tells them that this is a good idea, and I disagree. And this is why I have such problems with energy optimizers, because they get these ideas and they don't understand the inductive load concepts and motors and the whole bit. Like, they're not trained at that level. They don't know. They think they know more than they do, and that's okay. Most of us do. So it's so hard, because the facility is bought into most of what they're saying, and they see them as a higher authority than us as the field tech usually. So it's a really difficult conversation to have. Yeah, I've been there too many times. Air velocity failure on a Trane and telepack unit. Do you know where it is located? It's in the supply. Air velocity. That that sensor should be right in the supply trunk, just below the main feed as it leaves the RTU. Okay, MTT, make the time for your family, everybody. Hope you enjoy your Memorial Day. I'm going to wrap this up, and I'd love to work with you at Chiller Academy. I have free resources there through the free service training, and with just 8 minutes a day, the certification course is going to do a lot to help you. And then if you're already established and you're working on chillers, you just want more help, you want to improve your processes, that's where I would encourage you to the service training program. Those are step-by-step guides to take you through just what we do every day and help you take better, more effective, efficient processes. That is the goal behind the service course. Hope you enjoyed this. I'll see you all around.